So welcome back. So we were discussing different prompting techniques. We saw in the last lecture how to write prompts, right? What are the components of a prompt, right? What's prompt template? How it affects the accuracy? How the accuracy of the model increases with the increasing size of the model parameters for different types of prompts, and so on, right? So now let's discuss different advanced prompting techniques. So in 2022, people realized that if you just write few short prompts, like let's take a math reasoning question. Let's say Mohit has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? This is a question, and this is your answer. Then, so this is your one shot, right? And you ask this question: a cafeteria had 23 apples. If they used 20 to make lunch and brought 6 more, how many apples do they have? The output you expect is 9, but the model produces 27, because the model has been exposed to a pair which is a question and answer, the final answer. But the model doesn't know how to reason about it, right? So this is your standard prompt. But if you, instead of writing this, if you had written in this way, this is your question, and these are the steps. So Mohit started with 5 balls, 2 cans of 3 tennis balls, 5 plus 6 equals to 11. The answer is 11. So this is your example, okay? Then you give this question, right? Cafeteria had blah blah blah, and you see that the model will not only produce the right answer, but also the steps, right, required to produce this answer. And this new prompting technique is called the chain of thought prompting, COT. What are the thoughts here? The thoughts are, let's say in this case, the first thought is the cafeteria had 23 apples originally. The second thought is they used 20 to make lunch. The third thought is, so they had 23 minus 20 equals to 3, and so on. These are the steps, and this essentially mimics the way a human thinks, right? Now, surprisingly, in the COT paper, they also showed that if you don't have any example, right, you want to do it in a zero-shot manner, you just write, let's think step by step, okay? Write, let's think step by step, and then your question that you want to solve. Then also you see that the model will be able to decompose the problems into steps, and then each of the steps will be solved one by one. Okay, so after chain of thought prompting, people also suggested something called chain of thought with self-consistency. Here the idea is that you ask the same question to the models multiple times, and as all these LLMs are stochastic, right? Some of you know that these models are called stochastic parrot, right? Why parrot? Because these models mimic, right? So the way a parrot mimics what the parrot learns, here also the model mimics what the model learns during the pre-training step, right? They're not able to invent something new. That's why they are called parrot. And stochastic because they are not deterministic. The answers are always different for different instances of a single prompt. So you give the question which you want to solve. This is one set of thoughts. This is another set of thoughts. This is another set of thoughts, right? You have multiple sets of thoughts at different instances for a specific question, right? And then you have some sort of voting mechanism, right? Let's say this chain produced the output 9, this chain also produced the output 9, this chain also produced, let's say this chain produces the output 24, and so on and so forth. You have some voting mechanism. Based on the voting, you choose one of the thoughts, one of the sequence of thoughts, right? And of course this is not as simple. If you want to look at the paper, they also had some sort of a module which decides which chain one should essentially pick. Consecutively, the next model was proposed, which is called tree of thoughts, right? So in tree of thoughts, the idea is that it's kind of a branch and bound, right? So you start with a step, and then you explore all possible sub-steps, right? Now you take one of the sub-steps, you further explore this, and you keep on doing this thing. So you basically produce the entire tree, right, where each branch, right, from root to leaf would be your hypothesis, right, would be your thought. Okay, so here you need three components. One is called branching, other is called scoring, other is called backtracking. So branching module is responsible for deciding whether I should branch, I should split it into different branches or not. Scoring module evaluates a particular branch, right, and decides whether, and then there's a module called backtracking. It decides whether I should backtrack to the previous, right, the previous node, and then I should further branch out or not. Let's look at this example. So this is called this famous mathematics question called 24 guess 24 games. I don't remember the exact name, but the idea is that you are given numbers, right? Let's say 4 numbers, and you have to come up with ways to essentially result the number 24. Okay, let's say you are given 4, 9, 10, 13. Now what are the operations that you can do to obtain 24, right? Remember, when you do some operations between a pair of numbers, let's say you do addition 4 plus 9, which will result in 13. Now 13 will become one of the candidates into your possible numbers, right? So in this case, let's say you start with 4, 9, 10, 13, right? You have one branch which suggests you to subtract 4 from 10. So you have 10 minus 4 equals to 6, right? So you have exhausted 10, you have exhausted 4. So what else is remaining? You have the remaining numbers 9, 13 and the 6 that you obtain, right? So you can't use a number multiple times, by the way. Okay, so the numbers which are left are 6, 9 and 13. Now next step can be again subtraction. 13 minus 9, which will result in 4. So what are the numbers which are left? 6 and 4, right? The next step can be 4 times 6, which will result in 24. Now this can be one successful branch, right? You can also think of other branches. For example, you can say that, okay, I start with 4 plus 9, which will produce 13, and then you further branch out this thing. So you see here that you need a module which will decide whether to branch out or not. You need a module which will evaluate the quality, right, whether you are going to the right direction or not, right? And you need something which will help you backtrack. Let's say you have decided something, you have ended up generating something which your scoring function feels that is not correct. Now you have to backtrack. This is same as branch and bound kind of algorithmic setup. Okay, so this scoring, backtracking, branching, these are different modules, right? As you see here, and these are different language models, by the way. Okay, for example, here you see that the scoring module says that you have already generated 36, right? There is no way to obtain 24 with this such a big number, so you stop here. If you stop, right, if your scoring module says that you should stop here, you can stop and you can start backtracking. Okay, this is tree of thoughts. Now the obvious choice is that from chain of thought you have tree of thoughts. What next? Graph of thoughts, right? In graph of thoughts, the idea is that you know, you have you see here in the graph of thoughts, your chains, all these chains are connected, right? As you see, you know, this green green circles indicate that your scoring module says that this is a positive score, whereas you know, this kind of circle indicates that this is unscored, and red circle indicates that this is a negative score, right? So here also you start with an initial thought, and then you branch out, you can backtrack, you can refine, you can reuse some of the existing thoughts, and so on and so forth. Okay, so you need an aggregator which will decide whether two thoughts can be combined or not, like this. So chain of thoughts, one single thought, one single chain of thoughts. Chain of thoughts with consistency, self consistency, you have multiple chain of thoughts. Tree of thoughts, right? Now you have the capacity to essentially backtrack, okay? And you can score each of these thoughts, and then graph of thoughts, all these thoughts are connected, okay? And these are some of the advanced prompting techniques that people use. So far we have seen these models can take multiple types of prompts, but as I mentioned earlier, that they are highly sensitive to prompts, right? If you change prompts here and there, you will see the output of the models will change drastically. Now, so along with accuracy, there is another factor called sensitivity, which also corresponds to robustness. This needs to be measured, right? So how do you measure the given a data and a model? Can we measure how sensitive the model is with respect to the data? Okay, this is something that we will not discuss. Let's say you take Llama 3 instruct model, right, 8B instruct model, and you ask the model that how much are you familiar with principles of Buddhism, right? And it will say that Buddhism is a philosophy and spiritual practice that's originated in ancient India and blah blah blah, right? You ask the same question again, how much do you understand Buddhism? Almost the same question, right? But this time it says that 0.00001%, right? Just kidding, I'm not a Buddhist scholar either, right? You see, my intention was to ask the same thing repeatedly, but this time the model thought that kind of, I was joking. So this is something that you want to prevent, because if this happens, model will not become robust. Okay, so the question that we're asking is, by the way, this is the research that we have done in our lab, okay, very recently. The question that we are asking is whether accuracy is only a good measure or not. So far we have been only talking about accuracy, right, with the increasing size of the model, how accuracy impacts, and so on and so forth, right? And you see here that, you know, models like Llama 3, Gemma, Mistral 7 billion instruct, right, on across different tasks, MMLU, human eval, GSM 8K, these are all different reasoning tasks, right? People always report the accuracy, okay? But we said that accuracy is not enough. You also need to report the sensitivity of the model. Okay, how do we quantify sensitivity? Okay, so when we say sensitivity and accuracy, two things should be considered side by side. Okay, let's say I ask the model, do you know the capital of India? The model says the capital of India is Delhi. Okay, you again ask, I am not sure what the capital of India is, do you know? The model says yes, the capital of India is Delhi, right? You see, the model keeps on producing the correct answer and consistently. On the other hand, if you see that a model, if you ask the model that, do you know the capital of India? Model says yes. I am not sure about the capital of India, do you know this? Yes. Can you please tell me whether Delhi is the capital of India or not? Yes, right? So every time the model answers yes. So this is consistent, the model is consistent but not accurate, right? So you have model A whose accuracy is 85%, but sensitivity is also very high, 60%. If the model is more sensitive to prompts, the model is bad. So you want to decrease the sensitivity of the model, right? Model B, accuracy is 75%, lower than model A, but sensitivity is pretty low, 20%. So you should prefer model B over model A, because accuracy is almost comparable, but sensitivity wise model B is much more robust than model A, right? So we need a holistic measure to capture prompt sensitivity of language models for a more comprehensive evaluation of language models. So how to measure the sensitivity? So this is our question, right? Given a prompt along with its intent preserving variants, right? The intent of the variants of the prompt should remain the same, and the corresponding set of responses generated by the model. How do we measure the sensitivity of the language model on the given prompt, right? To quantify this, we came up with a new index called Posix. So Posix is a new new index to measure the prompt sensitivity of a model. Okay, and it's very easy to install. You just do pip install, right? Pip install prompt sensitivity index. You'll be able to install it. So the code is very handy. And this is the paper. It's a collaboration. It's a collaborative work with Adobe Delhi. Okay, so what do I mean by intent preserving prompt, right? Intent preserved variations. So let's say the question is, what is the capital of India? Okay, and your variations of your prompts are, what city serves as the capital of India? Can you tell me the capital city of India? Where is the capital of India located? What is the name of India's capital? Can you provide the name of India's capital? These are all different paraphrases of the same prompt. And you see, the intent of the prompt remains the same across all the paraphrases, right? And the hope is that if the model is non-sensitive, is not sensitive, is robust, it should always produce the same answer for all these variations. So in the metric, the Posix metric, the metric wants to capture these 4 different aspects, right? So how do you know that the metrics that we propose is actually of good quality or not, right? So we check whether the metric captures response diversity, whether the metric captures response distribution entropy, whether it captures semantic coherence, and whether it captures variance in confidence. I will discuss all these things one by one. Okay, what is response diversity? So given the prompt and different variations, I would like to see how the responses obtained from the model vary, right? Let's say model A, a Llama 3 8B, and model B, Mistral 7 billion instruct model. For different variations, model A produces different answers. So the same question, right? The answers are almost correct, but some cases, for example here, along with the answer, the model also produced the question, a new question, which is the following is the largest city in Delhi by area. Nobody knows why the model produces this, right? This is not expected. Whereas if you look at Mistral B, for all these different variations, Mistral B is quite consistent in terms of producing answers. Of course, in one case, it produces weird like a kind of MCQ answers. I don't know why, but still the answer is quite consistent. So you can say that model B is more consistent than model A. So model A is more sensitive than model B. More sensitivity is bad. Okay, this is called response diversity or response diversity. Yes, let's say there are 2 models with same response diversity, right? Model A also produces two different responses. Model B also produces two different responses, right? Now, how do you quantify? How do you quantify which one is better? The next one is called response distribution entropy, right? You look at the entropy of the responses. Okay, what does it mean? Let's say you have a prompt P and you have 5 different variations of the prompt, right? P1, P2, P3, P4, P5. Model 1, let's say it's a maths reasoning question. You want the model to produce a number. Let's say model 1 produces 2, 2, 2, 2, 3, right? Model 2 produces 2, 2, 3, 4, 5, right? Which one is more sensitive? Which one is more robust? Which one is more sensitive? So response diversity, response distribution entropy says that why don't you compute the entropy of the sequence and this sequence, right? This is bad. This is still okay, right? If you look at the entropy of this sequence will be lower and entropy of this sequence will be higher. If a model's response distribution entropy is higher, the model is more sensitive, which is bad, right? You see here, right? The model produces 4 different responses, but this response has been produced multiple times, whereas other 3 responses have not been produced that many of times, right? Whereas for B, things are all the same. So this entropy is high, this entropy is low, and this is more sensitive, this is less sensitive. Okay. Semantic coherence. I want that the responses that are generated by the model should be coherent, should be semantically same. If you look at the cosine similarity between the embeddings of the responses, should be the same, right? So higher the semantic similarity between responses, lower the sensitivity. Lower the semantic similarity, higher the sensitivity. Okay, and you want the semantic similarity to be higher in order to produce a robust model. Okay, so the fourth one is variance of confidence. Assuming that the response diversity is same for both the models, the distribution entropy is same for both the models, the semantic coherence is same for both the models, what else? You check the confidence, how confident the model was to produce those responses, right? And you look at the variance, right? And how do you do that? Simple idea, you look at log likelihood of the responses, right? Higher the variance, right? Higher the variance in terms of log likelihood, higher the sensitivity. Okay, and what the model is. So now let's look at our assumption. So we have discussed 4 criteria based on which we will judge the quality of our metric, right? Let's look at the assumption. So what do you want to achieve? Let's say I want my model to produce, so for 2 different variations of the prompt, let's say the prompt is, one variation is, can you tell me the capital city of India? What is the capital city of India? For 2 different variations of the model, the probability that the model will produce, let's say answer 1, this is answer 1, should be the same. Answer 1 is the star, right? What I'm saying, what I just said, let me rephrase again. This prompt, given this prompt and the paraphrased version of the prompt, the probability that given both the prompts, the model will generate the same answer should be the same. It can be answer 1 or it can be answer 2, but the probability will be the same. This is our assumption. Okay, let us now discuss the metric Posix. Okay, you are given a data D, you are given a model M, okay, and you have different intent preserving variations of the prompt, which is denoted by X, capital X, set, and the corresponding responses for different prompts is Y. Okay, so sensitivity of the model M on these different variations X is captured by, look at only this part. What is this? Probability of the model generating a specific response Yj given Xi and generating the same response Yj given Xj, right? This is Xi, this is Xj, right? And this is my Y. Given a Y, I take a pair of intent preserving prompts and I check the probability. Okay, you fix Y, not given, you fix Y, you look at the two variations of the prompt, you measure the probability and you take the ratio, and we expect that if they are the same, it means that the model is robust, is less sensitive, right? And it is, this quantity is normalized by the length of the response, right? And you have all possible pairs. So you do this for a specific model M, right? And the specific set of prompts, right? And then you have the entire data, right? You have many other prompts. Now remember, this is one, you take one prompt and you have different variations of the prompt. You have many such prompts, right? And D is nothing but the prompt data set, okay? And you essentially sum them up and then you normalize it by the number of such data points, right? The four criteria I mentioned earlier, look at this. Number of unique responses increases, the model is bad, sensitivity should increase. Here, this number, our Posix score is also increasing. The entropy is getting bigger and bigger, the model is getting worse and worse, right? And sensitivity is also increasing, right? So this essentially indicates that our metric is actually correct, right? Cosine similarity increases, meaning the models tend to produce similar answers, meaning sensitivity is less, our value is decreasing. Confidence variation increases, model is bad, and Posix score is also increasing. Okay, we tested across all different variations, right? A huge experimental setup was there. There are three different types of models: Llama, Mistral, and there. So Llama, Mistral, and Olmo, and their chat version and instruct version, base version and chat version, and we had different experiments. I'm not going into details of this, but bottom line story is that there is no clear-cut evidence that with the increasing size of the model, right, the sensitivity increases or not. In fact, we have seen certain cases that here, let's say, base versus chat, right? Base versus chat, there is no guarantee that a chat model, instruction fine-tuning model will be less sensitive, right? There's no guarantee. Similarly, we have checked with zero shot, few shot setup, and so adding few shot examples may help, but most cases it reduces the sensitivity. That is good. Okay, so that's it. We discussed advanced prompting techniques, how to capture the sensitivity of a prompt, right? And we also discussed different prompting templates. In the previous lecture, we discussed different prompting prompt templates and so on and so forth. So in the next lecture, we will start discussing alignment techniques, right? Reinforcement learning from human feedback method. Now we are moving towards the design of ChatGPT kind of model. We'll discuss what are the other components that were used apart from pre-training, fine-tuning, instruct fine-tuning, what else was used to build the ChatGPT kind of model. Okay, thank you.